on the board now I have a few things that are coming up, and you'll notice it says final quiz next Friday, 5/27. I know that's some of my, that's not what we want. Okay, some of my classes, or I didn't think I told all my classes, we were probably going to have a quiz this Thursday. Well, we decided we're not going to have a quiz Thursday. We're going to combine basically solutions and acids and bases into one unit, I guess. And so that final quiz is going to be next Friday. And then if you're doing your math, well, after that we still have, well, we have Memorial Day the next week, so we'll have class on Monday. We'll have class Wednesday, Thursday, Friday, and then the following Monday after that. So we'll have some other activities and things that we're going to do with your final quiz, and real materials are going to be done next week, Friday already, before Memorial Day weekend. Today, your titration lab is due. We're going to go over one question from number 6, just so we all understand what's happening there, and it kind of is a nice segue into the new unit on acids and bases. Solution stoic, that's what we're going to be talking about today. There was a couple problems of that on the sheet that you did on Monday, but we're going to go through a little bit today and make sure everyone's on the same page. That's going to be due Friday, and the acids and bases is on the back of the solution stoic sheet. That's going to be due on Friday as well. There's not a whole lot with that stuff, you guys. It should be relatively easy for most of us. So today what we're going to be doing, we're going to go through solution stoichiometry. We're going to do the first 2 problems on your worksheet together. So that's why we don't have a note sheet for that. And then we're going to kind of have an intro to acids and bases and go through, what is an acid, what is a base, what makes those up. Okay. All right. So today then, to start out, we're just going to do the first couple problems on that sheet. We're going to go through solution stoichiometry. This, you guys see this flow chart all year. We use it with moles to grams and moles to particles. We added moles to liters. So each unit we're kind of adding a new piece to this. This unit, what we've added is this guy on top here, this triangle that we're going to use for molarity, and it lets us go from moles of a solution to liters of a solution. So that's what's going to be new for the solution stoichiometry for this part. So I'm going to go through 2 types of problems that you guys can see, where one where we have to start with it and one where we have to end with it. Okay, so this first one says, how many liters of 0.500 molar potassium chloride solution is needed to react with excess silver nitrate so that 5.76 grams of silver chloride will be formed. So the first thing we're going to do is just write out the balanced chemical equation here. So we have potassium chloride, it's KCl. And that's aqueous, plus silver nitrate, that's AgNO3. That's also aqueous. And they're reacting to form silver chloride, that's AgCl, that's a solid, plus potassium nitrate. And that is also going to be aqueous. Alright, so then, problem, it says, how many liters of 0.50 molar potassium chloride? So, I want to know how many liters, question mark, and it's 0.500 molar. It's needed to react with excess silver nitrate so that 5.76 grams of silver chloride is formed. So really we have to figure out, okay, when are we going to be using this, and when are we going to be using our flow chart and use T-charts? Well, it's easy to be able to figure that out because here we're not given a value for liters, right? So we only have really one part of this triangle. If we only have one part, well, we obviously can't solve for that to start. So it means that what we're going to end up having to do is we're going to have to start at 5.76 grams of silver chloride, and we need to figure out how many moles of potassium chloride there are. So we're going to start out with 5.76 grams. And that's AgCl. Okay, and by now you guys know what comes next down here. We got to put the molar mass on bottom, and we got to put number of moles on top. So the molar mass of silver chloride, it's just silver plus chlorine, so it's going to be 143.4 grams. And that's in 1 mole of silver chloride. Okay, what comes next is just the mole ratios. The mole ratios for here are easy. They're all 1 to 1. So it's 1 mole of AgCl for every 1 mole of KCl. So that's what we're trying to get our moles of. So I have 1 mole AgCl on bottom and 1 mole of KCl on top. And we're good there because then we're at moles of KCl, and we can use it to plug into our equation to find how many liters we have. So essentially all we're doing here is taking 5.76 grams of silver chloride and dividing it by the 143.4 grams of the molar mass that it has, because everything else is 1s. It's 1 to 1 ratio. So we take 5.76 divided by 143.4, and we're going to get 0.040 moles. .040. Oh shoot, you're right. Thank you. Yeah, there we go. Which isn't really a decimal point, you know. Thank you for catching that. Yes, it's 0.040. So now we're at number of moles. We can use this formula to figure out how many liters we have. So we have 0.040 moles in the amount of liters that we want equals our molarity, which our molarity is 0.500 molar. Okay, so now this is where we want to use our triangle here, and we see that if we're trying to get from, if we have moles and a molarity and we want liters, we take moles divided by our concentration. That's going to give us how many liters we have. So we have 0.040 moles divided by 0.500 molar, and that's going to give us 0.08 liters, and that's of the potassium chloride. So it's like 80 milliliters. So we circle that. That's our final answer. Questions on that first one? Okay. We're just going to do number 2 then, and then you guys will have the rest of the sheet to do. No. Yeah, the rest of the class will do 5 problems. No. All right, so moving on. You don't have a balanced. If you look down there, you have balanced chemical equations for the rest of them, but we're just going to write these out together to start. So let's take a look. It says, what mass of aluminum hydroxide is required to completely react with 50.0 milliliters of 0.255 molar sulfuric acid? So we got aluminum hydroxide, AlOH3. Aluminum's charge is 3 plus. We're adding that to sulfuric acid, so H2SO4. Now, when those two react, we're going to get aluminum sulfate and water. And we need to balance that out. So we're going to need 2, 3, and 6. Okay, then it says what mass of aluminum hydroxide. So I'm trying to find grams of aluminum hydroxide, and it says it's required to completely react with 50 milliliters of 0.255 molar sulfuric acid. So underneath here, right, 2.00, and it is 0.255 molar. So when you're given two values for a solution, you guys, it means that you're going to have to start out by using this equation. Okay, so you're going to have to figure out moles right away. And when you're asked to find something else, if you're asked to find liters, that's when you do this at the end. But if you're given two values here, you know that you're probably going to be starting with that for the equation. So you're not going to have to start in a T-chart. So to start out, you'll have 0.255 equals moles divided by, now we don't write 50 in there, we got to write that number of liters there, so it's going to be 0.050 liters. So we got to divide that by 1,000. And if we look down here, we need to do the concentration times the liters. That's how we're going to get how many moles we have. So we're going to take 0.255 times 0.05. That's going to give us 0.0128 moles. So that's how many moles of the sulfuric, of this H2SO4 would be in that sulfuric acid solution. So I'm going to write moles H2SO4. So Dustin, what's the next step? What do I have to put down here? Is it 1 mole, or what would I put down there actually? What's the next part? Huh? 3 moles, right. 3 moles H2SO4. Somebody else. Francis, what goes on top of that? What are we trying to get to? This is the aluminum sulfate, right? So somebody help her out, and we're trying to get to aluminum hydroxide, right?
So it's 2 moles.
Right. So it's 2 moles AlOH3. Good. Okay, now we're at moles of that. Somebody else, what goes down here now? Right, 1 mole of AlOH3. And Libby, what goes on top here? Right, the molar mass. You don't need to add it up. I got it written down. Yeah. Yeah, the molar mass. So it's 78 grams of aluminum hydroxide. So you guys know what comes next. You're just going to plug these all into your calculator, multiply by everything on top, and then divide by the 3 on the bottom. You're going to get 0.655 grams of the aluminum hydroxide. Does anybody have questions on that? I know right now that we did 2, we went to grams, but I could have asked you to go to particles of aluminum hydroxide. So at the end you would have had Avogadro's number on top. I could have, we could start out with liters of a gas and figure out what you need in solution. We can do any of those things. You just need to know basically how you use the flow chart and how you use our molarity equation. If there's no questions on that, you guys can just slide that away for a second and take your notebooks out. We're going to do some things with acids and bases now, and you're not going to need that for a little bit. Alright, this is just going to be our basic little introduction to acids and bases. We're going to talk, so I'm going to go through some definitions of what an acid is, what a base actually is. We're going to talk about pH and some things like that tomorrow and Friday. So today we just want to get comfortable with what these things actually are. We have a couple different definitions up here. The one that we're really going to use most of the time is this Bronsted-Lowry, but I'm going to give you an Arrhenius acid definition too. An Arrhenius acid, it's a little more specific. It's anything that produces H+. And what I mean by H+ is just a hydrogen ion, which essentially is just a proton. And I'll show you that on the Bronsted-Lowry part in a second. And so Arrhenius base is anything that produces OH-. We're going to use the Bronsted-Lowry definition. It's a little bit more comprehensive. And what the Bronsted-Lowry definition says that anything that donates an H+ is going to be an acid. So when I say H+, I have proton in parentheses underneath there because if you look at this picture here, you have a hydrogen atom on the left-hand side. If we take its electron away, the only thing that we really have left is the proton that's in its nucleus, right? So essentially, when we say H+ and we say proton, they mean the exact same thing. We can use those terms interchangeably. Okay. A Bronsted-Lowry base is anything that's going to accept that H+. So acids and bases, we know that they're going to react, and when they're reacting, really what's happening is that this hydrogen, this H+, is being transferred from the acid to the base. That's an acid-base reaction. It's not anything more complicated than that. And so we're going to talk about identifying acids and bases and stuff in reactions, and it's all going to focus on that flow of hydrogen, the flow of that proton from one thing to another. Here's the reaction that you guys did in your titration lab. So during the titration we did an acid. We used an acid and a base. We used phenolphthalein to tell us when the reaction was complete. Okay. Here I'm just going to identify what is the acid, what is the base in this reaction. So what we want to look at is we want to look at which one's giving away. I know we know this because we know what hydrochloric acid is, but we want to look at which one's giving away a hydrogen and which one's accepting the hydrogen. So in this case, that's why I have it in green here. This chlorine, this HCl, is going to be essentially donating that hydrogen and giving it to that OH. So that's what we call a proton donor. So acids are always, always, always proton donors. Bases are always proton acceptors. Okay, so this one is going to be the strong acid. You're going to hear me say strong acid, strong base, weak acid, weak base. We're not going to get into what that means all that much. We just need to understand that really the strength of acids, it doesn't have anything to do with how dangerous they are, for lack of a better word. It has to do with something else that we'll talk a little bit about later. So we saw that the chlorine, the HCl, that's the proton donor, but we need to find out what the proton acceptor is, or what's receiving that proton. Okay, so in this case, that OH group, the one with the sodium on the front, that's going to be what's accepting that hydrogen. It's getting the hydrogen. So we call it the proton acceptor, and that's what's going to make that the strong base in this case. It's easy to see up here when we have a strong acid reacting with a strong base, we know that they neutralize, right? You guys have heard this term like neutralize all the time. So when we spilled acid in the lab, we threw a little baking soda on there because it's a base, and we said that it's safe to clean up. The reason it's safe to clean up is because all we've really created here is water and a salt. In this case, it happens to be table salt, which we know is already table salt. But any strong base with the strong acid is going to create salt. So it could be different salts here. It could be KCl if we use potassium hydroxide. It could be strontium hydroxide. It could be anything like that. But it's going to create water and a salt. So that's obviously we can see that then it's safe to clean up, and that's why we say it's a neutralization reaction. Okay, so if we're looking at this reaction right now, really, there's only two parts of this reaction that we really care about. we care about the hydrogen, where that's going, and we care about what's accepting the hydrogen. So we care about where the ions are going, because that hydrogen right now, that H+, that's considered an ion. Okay? And what's accepting it is also considered an ion. So we can get rid of everything else, and we can come up with what's called a net ionic equation. And that's going to track just those key parts of it. So what's really happening is we have an H+ on one side and OH- on one side, and they're joining together to make this HOH, because this H+ is really what's making HCl acidic. This OH- is what's making NaOH basic. Okay, so when they combine and neutralize each other, they're just creating water. So the flow of those ions is really what we're talking about when we're considering an acid and a base reaction. The next slide we're going to go through, I think it was number 6, and it is number 6 on your lab, and it's asking you about why the pink color stayed did ask you why the pink color stayed longer and longer, and hopefully this is going to kind of show you a little bit more clearly why that was. So this is your flask, okay, after you added acid to it. So you added the acid to it, and now if we go back to this net ionic equation, remember we're not caring about it as HCl right now, right? All we care about are these H+ ions that are in your acid. So that's why all I have in solution here is H+ ions. I'm going to add base to it, and when I add the base to it, the NaOH, all I'm going to add is the OH-, because that's the only part we care about, okay? Is that ionic part. So now we have H+ in that solution. Now, when you first started titration, you drop this OH- into the solution. And you can see what happened right away is that it might just flash pink right away, right? Just for a second, and then it went away. The reason it went away so fast, you guys, is because there's lots of, when we first start the titration, there's lots of these H+ in the solution, okay? So they can really easily attract and find that OH, and they bond together right away. So that neutralization occurs really fast and really easily. So it might have flashed where that OH- was for a second, but as soon as H+ attaches to it, well, that's not basic anymore, right? Now it's water. So now it's not going to be pink there anymore, because phenolphthalein, what we added to it, it turns pink only when there's a base there. Okay? So once that happens, it's gone. Now, we kept adding OH, so we add another OH-, but you can see the H+ are a little bit further away now, so it might have stayed pink for a little bit longer, right? But we swirled it around a little bit. That allowed those H+ to get close enough where they bonded to that OH-, okay? And then they're disappearing because now they're water. And so each time you can see that there's a little bit less H+, a little bit more water there, and it takes a little bit longer for that neutralization to occur. So at some point, the pink color starts staying longer and longer and longer. And finally, the last time, it might have stayed pink for quite a while. And then you had to really swirl it. And all you're doing when you're swirling it, you guys, is you're creating an opportunity for this H+ to find these OH- and basically neutralize. Okay? Because if you don't swirl it around, there's no way that these are like moving around in solution by themselves, right? Like they need to be mixed by you. So when you swirl it, you're creating an opportunity for them to attach onto each other. It neutralizes out. Now at some point, it's neutral. Okay? It might still have been clear if there's no extra OH- in that solution. So that's why when you added that one extra or that couple extra drops of OH-, well, now the solution turns pink and stays pink when that happens. Okay? Because now there's no more H+ in that solution to bond and neutralize it out with. So now that solution stayed pink like that. Okay, does anybody have questions about that or any of the other things on the lab? All right, beautiful. You're going to need to write this stuff down that I'm about to go through right now. This is an acid-base reaction. We're going to go through one acid reaction with water and a base and its reaction with water. And it's really just an acid in solution with water and what that looks like, and a base in solution with water and what that looks like. And we're going to go through a couple different parts of this reaction. So in every acid-base reaction, we have names for the acid and the base, and we have names for what these compounds are called on this side too. And so we're going to be able to need to identify the different components of this reaction. Okay, HA, what that's standing for right now, is just a generic acid. So A literally is acid. The H is just showing you where that proton is, where that hydrogen is on the acid. So it could be HCl, it could be HBr. This A could stand for the SO4 group that's on acid sometimes. It's just supposed to be a generic acid right now. So it can stand for all of them. Okay, H2O in this case is going to be our base. And we'll see that water can act like an acid, or can act like an acid, or can act like a base depending on what it's with. So in this case, it's in a solution with an acid, so in order to have an acid-base reaction, something has to be the acid, something has to be the base. And so in this case, water is going to act like a base. In the next reaction that we're going to do, it's going to act like an acid. So how do we know which one's which? Well, we're going to be tracking this hydrogen. Okay? So right now this H8 is a proton donor. How do I know it's a proton donor? Because it has a hydrogen on this side. On this side, no hydrogen. Okay? So that means it's giving a hydrogen away. So this A and this A, they're kind of a pair together. And what we call this A on this side now is we call that a conjugate base. And what a conjugate base is, it's what's left after an acid has donated a proton. And the reason we call it a conjugate base now, you guys, because if you look here, we have this reaction arrow. I know we don't talk a lot about these, but it's saying that the reaction goes both ways. So on this side it's going to act like a base, on this side it's going to act like an acid. Okay, but how we find out which one it is, it's just whatever's left after that acid is donating a proton. So now you see it has a negative charge. Okay. This H2O is paired with the H3O plus on the other side. So if the A minus is called a conjugate base, you probably guessed that the base is always paired with what we call the conjugate acid. It's a proton acceptor. So it's accepted that H plus, and after it accepts that H plus, we call it a conjugate acid. And a conjugate acid is just the compound or the ion that's formed by receiving a proton. So it's on this side, it's now received a hydrogen. You can see there's 3 here, there's 2 here, so it's got an extra hydrogen. We call that a conjugate acid. So important things to realize right now, we have always an acid and a base on both sides of the reaction. So we have the acid here, base here, and here we have the conjugate acid, conjugate base. Another thing is that the acid is always paired with the conjugate base, and the base is always paired with the conjugate acid. So if you're having trouble identifying those, if you remember that, it'll be a little bit easier for you to identify these. All right, we're going to move on to another acid-base reaction. This time, well, let's just take a look. Let's figure out what's happening here. We need to figure out which one's the acid and which one's the base. What's our conjugate acid and what's our conjugate base? So if we look at this problem between HS minus and H2O, one of these is an acid and one is a base. Okay? The one that's the acid is the one that's going to be donating a hydrogen. The one that's the base is going to be the one that's accepting the hydrogen. So which one's going to be the acid and which one's the base in this case, you guys? So look, which one is giving away the hydrogen first, I guess? Which one's the acid? Huh? Look at from this side to this side, okay? Did it gain a hydrogen or lose a hydrogen? That's all you really need to look at. That one gained a hydrogen. So if it gained a hydrogen, that's a proton acceptor. So what does that mean that it is? The water's the acid, right? And the HS minus is the base. Okay, this is a base. Why? Because it's gaining a hydrogen. The water is the acid. Why? Because it's losing a hydrogen. It's donating a hydrogen away. Okay? This acid and this OH minus, so the H2O and the OH minus are making an acid conjugate base pair. So we call that the conjugate base because it's what's left after the acid donated a proton. Okay, the H2S is the conjugate acid because it's what's formed by receiving a proton. So the H2S got the proton in this case. Okay, we're going to go a couple examples of this. It says identify the following as acid, base, conjugate acid, or conjugate base. So you can write this down if you want to, otherwise you can just follow along as we go through it. First of all, we probably already know which one's the acid and which one's the base just because we are familiar with one of the compounds on here. But we have to, when you don't know for sure, and you're just looking at this, you have to decide, okay, where is the hydrogen going? That's really all you're tracking right now. What's happening with hydrogen from the left side of the equation to the right side of the equation? So if you look at HCl, is chlorine here, is it gaining or losing a hydrogen from the left to right side? It's losing, which means that we can say that it's donating hydrogen. So the thing that donates the hydrogen is called what? The acid. Okay? What is chlorine? What's the thing called after it's donated? That's called the conjugate base. So on this side, remember the acid, conjugate base, always pair together like this. Okay, so what's left then, I mean by default NH3 has to be a base because you have to have a base reacting with the acid, but if we didn't know that, we could also see, okay, from the left to right side, it's accepted a hydrogen. So that makes it a base. After it's accepted a hydrogen, it is called a conjugate acid. Okay, so that's how you're going to go about doing these. I mean, there's that whole chart on the back side of your sheet on acid, base, 1. That's all determining acids, bases, conjugate acids, and conjugate bases. Okay. So if we do one more of these, now we're going to look again. Remember, we just want to know where are the hydrogens going. So in this case, which one's donating hydrogen? Remember, you have to look at from left to right. So HCN, exactly. HCN is donating hydrogen, so it's what, Dustin? Right. And so which one's accepting a hydrogen? Huh? No, which one on the left side? Sorry. Which one is accepting a hydrogen? Here. Is going to accept it. The OH minus, so that's the base. So this is the base. It's always paired with the conjugate acid. Okay? This is the acid. It's always paired with the conjugate base. Okay? It's easy to see the conjugate bases and conjugate acids like that. This type of problem you're going to have, it says write the conjugate acid for the following. So now you have to understand what a conjugate acid is. So you have to know that a conjugate acid and a base are paired together. Okay? So I want to know what's the conjugate acid for these guys. That means that I'm working with a base here and here. So if something's a base, it means it needs to accept hydrogens. So really all I'm doing here is deciding, am I adding a hydrogen or taking a hydrogen away? So if I want to know what the conjugate acid is from these bases, all I need to do is add a hydrogen. So for number 1, I have PO4 3 minus. If I add a hydrogen, it becomes PO4 2 minus. Okay, so what about S2 minus? What if I'm going to write the conjugate acid for that? Remember, I'm saying these are bases right now, and what do bases do? They accept hydrogen. So what's the conjugate acid for this S2 minus base? Huh? It's just
HS.
It's just H, S minus. You're just adding one hydrogen. If it was H2S, you would have added 2 hydrogens, but it's just HS minus. Because all we're doing is adding a hydrogen here, okay? So when we're working with a base, remember we're adding hydrogens. The next one, it says write the conjugate base for the following acids now. So I'm giving you an acid here. I want to know what the conjugate base is for that acid. What do acids do? They donate protons. They donate hydrogens. So all we're doing for this one is taking away hydrogens. It's literally just the opposite. So when we're working with HClO3 and we want to know what the conjugate base is for that acid, we just take a hydrogen away. So it becomes ClO3 minus. Okay, number 2 is NH4 plus. NH4 plus is an acid. It's going to donate hydrogen, so the conjugate base for that acid is going to be just NH3. It has 1 less hydrogen. Questions on that right now? All right. We're going to have to know strong acids and what strong bases are. You're not going to have to know really what weak bases, weak acids, whatever. You need to know these guys though, okay? And all you need to know about what a strong acid is or what a strong base is it's something that 100% disassociates in solution. All that means is that it breaks up into parts in solution. Okay, so a strong acid will completely break apart. So, for example, HCl, when it's in solution, it'll completely break up into H plus and Cl minus. Weak acids and weak bases do not do that. Other ones are hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric. All those are going to be strong. That's ClO4 down here on the bottom. But you do need to know those. Okay, strong bases then are a little bit easier to remember. They're just group 1A plus OH, so that means all these guys minus hydrogen, that makes water. Okay, water's not a strong base. But those plus hydrogen. So an example of that would be NaOH, or sodium hydroxide. Other strong bases are going to be group 2A plus OH. But it's not all group 2A, it's just calcium, strontium, and barium. How you can remember it is just by thinking CBS. So no magnesium, no beryllium, just calcium, strontium, barium. An example of this would be barium hydroxide. Okay, we just have a little bit left here. This is acids versus bases in water, so this is what we did, the reaction that we did before. I'm not overly concerned with you writing this whole thing down again, you guys, right now, but I just want you to understand something on here, and you might need to write just part of it down. But if we look at these two reactions, now one is an acid, and it's in water, and the other one is a base in water. And it shows us what makes things acidic and what makes things basic. Okay, and what it really boils down to are these two ions right here. So if you notice, when I put an acid in water, what happens is that acid breaks apart into A minus, which is just the acid part, plus H3O plus. What's really giving it the acidic properties is this H3O plus. That's called a hydronium ion. So when we calculate things like pH, we're focusing on the concentration of this ion. So the more acidic something is, the more of this is going to be in solution, or the lower the pH would be. Okay, now when things are basic, if you look, there's a difference between that and the base, right? In the base, it's taking a hydrogen from water, so we get this OH minus in solution. Okay, that's called the hydroxide ion. And that's what's really making things basic. So when we talk about acids versus bases and things being basic versus acidic, what we're really doing is we're measuring these concentrations against each other. So the more OH minus something has in solution, the more basic it'll be, and the more H3O plus something has in a solution, the more acidic it'll be. Okay, and we're going to talk more about that on probably tomorrow and Friday. Okay. All right, we have about 10-ish minutes left. The next few minutes, we're going to watch a video on, it's basically on pH in your body, you guys, so it's going to explain why drinking diet soda is still bad for you. So it has to do with the pH of it.
the end of this short lesson, you'll be able to explain the answers to the following questions to your friends. Why are acid reflux medications one of the fastest growing groups of medications in the US? Why is it that Americans have the highest calcium consumption in the world, yet poor bone health? How can a diet soda with 0 calories make you gain weight? Here's the second thing that'll change your life. Are you ready? Every food or beverage is alkaline, acidic, or somewhere in between. Alkalinity and acidity are measured in terms of pH, which stands for potential of hydrogen. This is a pH scale. It ranges from 0, the most acidic, to 14, the most alkaline. For example, let's consider the following pH values. Your stomach acid is 1. Diet soda is 2.5. Coffee 3. Water 7. Your blood ranges from 7.35 to 7.45. Seawater is 8.5 and baking soda is 12. Ideally, human blood should be slightly alkaline, between 7.35 and 7.45 on the pH scale. Your body won't allow your pH to become imbalanced. If it did, you would die. Your body has built-in mechanisms such as respiration, perspiration, urination, and mineral depletion, which keep it in balance. The trouble begins when your body has to work overtime to maintain balance. An imbalance is primarily due to the overconsumption of acid-forming foods and beverages, as well as unhealthy stress. We consume considerably more acid-forming than alkaline-forming foods and beverages. We consume too much coffee, caffeine, soda pop, beer, alcohol, processed foods, fried food, high fructose corn syrup, sugar, artificial sweeteners, and animal proteins, just to name a few. In addition to our unhealthy food and beverage choices, we live in a world that keeps speeding up, potentially leading to high levels of unhealthy stress, which also increases acidity. Foods and beverages run the gamut of the pH scale. There are a few general rules. Animal products are for the most part acidic. Let's look at ice cream, cheese, yogurt, beef, lobster, chicken, pork, shellfish, venison, and fish. Vegetables and fruits are primarily alkaline. Let's look at snow peas, spinach, tomatoes, lettuce, squash, potatoes, cabbage, broccoli, asparagus, and sweet potatoes. And fruits, let's look at oranges, bananas, grapes, cherries, grapefruit, mangoes, raspberries, watermelons, lemons, and limes. I know you're thinking we got this wrong. Lemons and limes are acidic, right? Well, the classification of whether a food or beverage is acidic or alkaline is based on the effect it has on the body after digestion. For example, lemons are extremely acidic in their undigested form. However, their end product after digestion is more alkaline, making lemons alkaline forming in the body. A simple way to increase the alkalinity of a glass of water is to add a slice of lemon or lime. Let's see where popular drinks fall on the pH scale. We have soda, beer, coffee, alcohol, and tea. And how about water? Well, let's look at distilled water, bottled water, spring water, and mineral water. Another general rule is the more processed the food, the more acidic it will be. However, just because a food or beverage is acidic doesn't mean it's unhealthy. Blueberries and walnuts are both acid-forming foods, but they have tremendous health benefits. It's more important to pay attention to the overall trend. Remember when we said Americans eat a diet rich in acidic foods? Let's examine some typical American meals. How about a burger, french fries, and a soda? Or a steak, baked potato, and glass of wine? Or what about fried chicken, baked beans, corn, and a beer? Or the all-American picnic of a hot dog, potatoes, and a salad, and soda? These meals force your body into an acidic state. So let's bring this all together. What happens when your diet is too acidic? As previously mentioned, your body is constantly putting mechanisms in place to maintain a balanced pH. When your body has to work overtime to maintain balance, the trouble begins. As the blood becomes too acidic, less than 7.3 or so, mechanisms kick in to bring the blood pH back to about 7.4. The breathing rate increases to remove carbonic acid by exhaling carbon dioxide. The kidneys increase the acidity of the urine. Minerals begin to be leached out of the body, and the blood pH is quickly back to normal. Here's the kicker. To compensate for an acid-forming diet and high levels of stress, the body uses alkaline-forming minerals such as calcium, magnesium, iodine, potassium, and sodium. Well, that's good, right? What's the problem? The problem is that by eating diets rich in acidic foods, Americans are forcing their bodies to use these precious minerals to achieve balance. Let's take a look at some health problems related to an acid-forming diet and high levels of stress. One of the fastest growing categories of medications in the US are medications that relieve acid reflux. These medications relieve the discomfort, but are they truly fixing the problem? Ask yourself, why do I have acid reflux in the first place? Acid reflux medications are simply introducing alkaline-forming compounds in your body to counteract an acid-forming diet. This program has helped many people completely do away with acid reflux medications simply by improving the quality of foods and beverages they consume. The US has one of the highest calcium intakes in the world, but still has poor bone health when compared to other countries. Why? If we're consuming enough calcium to keep our bones healthy, what's the problem? An acid-forming diet forces your body to leach alkaline-forming minerals, such as calcium, to neutralize the pH of your blood. One of the major culprits is the overconsumption of acidic beverages, such as soda, coffee, energy drinks, and alcohol. And what is the #1 source of calories in America? Soda pop. The average American drinks over 46 gallons per year. Many people might say, "It's okay, I drink diet soda." We've heard of people having maybe 3 or 4 or even up to 10 diet sodas a day. Why not? There's 0 calories, right? What if the very thing that you thought helps keep weight off actually put weight on? How? Diet sodas, as well as regular sodas, contain phosphoric acid. Phosphoric acid is right next to battery acid on the pH scale. Constantly flooding the body with an acidic beverage, as we now know, results in the leaching of many minerals. We discussed the leaching of calcium, but now let's focus on iodine. Iodine helps support the health of the thyroid gland. Without iodine, the thyroid cannot work properly. One of the main functions of the thyroid is to regulate the body's metabolism. If you have an underproducing thyroid, your metabolism can become sluggish and weight gain can follow. And that's how a drink with 0 calories can cause you to gain weight. So tell me, how do I balance my body's pH? It's simple. 2 things, R&R and proper diet. First, rest and recovery. Take time for yourself. Get more sleep. Take regular vacations and try to get a little downtime each day. Secondly, diet. Consume foods and beverages that have high alkaline levels. Now, there's no need to memorize these foods we presented. In the attachments tab in the upper right, you'll find the food target.